See now, so let me start our meeting. Today, let me welcome our speaker, Sven Wiedemeyer, and briefly introduce him. He got his PhD in astronomy in 2003 from University of Kiel in Germany. He worked as postdoctoral research fellow in Kippenheuer Institute for Solar Physics, 2003 to 2006. He did simulations and observations of solar atmosphere. Then he went as Marie Curie Inter-European Fellow to University of Oslo, where he is now as a permanent staff, and he also one of the PIs of Rosland Center for Solar Physics, which is Center of Excellence at the University of Oslo, and he also active member for simulation network for ALMA, and he founded Salmon Network a few years ago, which helps solar ALMA observation and interpretation and simulation of this. So I'm glad to welcome Sven to give the talk today. And a couple of reminders for participants, but I ask to keep microphone muted. And if you have to ask questions during the talk, please send questions using chat mechanism to me, and I will interrupt speaker and ask him question. And in case I feel that something unclear and a parameter not defined, I will interrupt speaker to ask such simple questions. Otherwise, we will keep questions to the end of the talk in 45 minutes from now. So please, Sven, go ahead. You have 45 minutes for your presentation.
Yeah. Thank you very much for giving the opportunity today to present an overview over the modeling and the challenges of modeling the dynamic chromosphere of the sun. So I'm trying to give some overview, but of course this is by no means a complete overview, but more meant as an illustration of where we have come from and where we are going. When here's an overview of my talk. So I thought first it would be worthwhile to have a look at observations and ask ourselves what exactly is the chromosphere of the sun, what do we observe, and what are the challenges here. Then we'll talk about some general considerations when it comes to numerical modeling and present a few examples of chromospheric models. And also, since ALMA is a research focus I'm working on lately, I will also give an outlook on ALMA related science in the very end. So when we talk about the chromosphere, we could actually start asking ourselves what exactly is the chromosphere and how is it defined. So if we try to define it very literally from the Greek origin, so then it's basically defined as the colored rim around the sun which we see during a solar eclipse. And this light which we see in these moments is mainly due to the H-alpha line, and that would define in this framework the chromosphere as the layer in the solar atmosphere from where the H-alpha emission originates. We could also take another perspective and talk about more based on what we know today, based on the average temperature certification of the sun, as you can see it here illustrated. And then we could say the atmospheric layer, that is the chromosphere atmospheric layer, that's above the photosphere, and in that sense above the temperature minimum. And on the upper end, it's defined by the sharp temperature rise to Coulomb values in the transition region. Then we would have then roughly temperatures about like 3,000 to a few thousand Kelvin. However, that's based on average certification, and of course a lot of assumptions go into that already. So probably the better definition would be in the end to really try to tie this to physical properties of the plasma that constitute the chromosphere. And in that sense, the chromosphere would be the atmospheric layer, which is clearly out of relative equilibrium, and where hydrogen is still mostly found in its neutral form, as opposed to the upper layers where it's mostly ionized. So already here, already defining the chromosphere is not straightforward and can lead to some confusion. And this is not so surprising if we look at observations, at modern observations, for example, here from the SDO satellite that shows us in the layer of this atmosphere, and we clearly see the atmosphere is highly dynamic, the structure is very intermittent, but also the different layers, if you want to call it like that, are clearly coupled dynamically. So we can't really look at one layer isolated, but we really have to consider the full atmosphere to, if we want to try to understand what's going on. A further complication is that we see structure in a very extended range of spatial scales, down to the current resolution limit that we can achieve, so it's about like 0.1 arcsecond, but also structures which span significant parts of the solar diameter. And the same is true for the timescales on which we see the sun evolving. So we have features like that evolves on the terms of days, or weeks, active regions, for example, down to timescales of a few seconds or so. There are a lot of different processes, physical processes going on at the same time. And in that sense, also the solar chromosphere can be understood as a fantastic plasma physics laboratory where we can learn a lot. So here are now observations that were done with the Swedish 1 meter solar telescope. And here you see a time series of images taken at the line center of the 2002 line at 1854 nanometers in infrared. And you clearly see here there's a lot of dynamics going on. The structure is very complicated. You see a few things that seem to be rather stationary, which is connected to magnetic fields. You have some fiber-like structures, and you have also some mesh-like pattern overlaid or underlaid to this, and even some swirling motions sometimes. So clearly the impression you get here is that this is a very, very complex phenomenon. And this is also true, or it's even more impressive if we look at the H-alpha line. Again, this is a time series taking up the line center of this line. And here we have even a stronger impact of the magnetic field that is structuring the emission that we see here. So you see a lot of elongated fiber-like structures where the plasma is following magnetic field lines. It gives this very, very complicated structure. Here you can even see a small flare going off. So a trick that we usually do when we observe, we try to not observe at one wavelength, but we try to observe at many different wavelengths and many different spectral indicators, because they are formed at different heights in the atmosphere and give us usually different information about plasma properties. Here we see 3 panels, 3 different line positions in an observation of the Classic 2K line. Again, done with the Swedish solar telescope with the chromosphere instrument here. And we see in the bottom right the continuum image, which is formed lowest in the atmosphere. So you basically see the granulation at the bottom of the photosphere. Then in the top left, you see a line ring position, which is formed well above the photosphere. So you see the chromosphere here. You will see the fiber structures here, and you see a mesh-like pattern there. And finally, in the bottom left, you see the line core maps, which look again different. They have more fibers. They have a stronger impression of magnetic field. So clearly from that you could argue that you would get an approximate qualitative picture of the height structure, right? So here is another representation of that from a similar data set, and this is stacked up to give a very nice illustration of what it means to observe at different wavelength positions, which on average at least are formed at different heights. So if you look at it like this, you could try to derive, qualitatively at least, the 3D structure of the chromosphere. However, as nice as this is for illustration purposes, we should not misunderstand that this would be a stack of flat layers. It's a bit more complicated than that, and because the chromosphere, the plasma in the chromosphere, it's not fully opaque, it's not fully transparent. It really much depends on the wavelength, for example, we're looking at. And that means that also different parts of the atmosphere are usually coupled by the radiation, which makes it a non-local phenomenon. And certain spectral features are formed then over very high extent height ranges. And that makes it very complicated, very difficult to interpret what we are actually observing when looking at such a map as we see here below. Even worse, this also produces something that you could call a diagnostic problem. So first of all, we have very few suitable diagnostics which we can use to observe the chromosphere. And most of those are very difficult to interpret because their formation involves many deviations from the equilibrium conditions. For example, the ionization degree in the chromosphere deviates from equilibrium, and of course you also have non-local thermodynamic equilibrium conditions there. And this gives us some nonlinear relations between what we observable, and the actual plasma property that we want to derive.
Sven, could you comment basically what is the difference between the term non-equilibrium effect and non-LTE, which is also sort of non-equilibrium? Just to clarify terminology, if you can. Yeah.
Well, I mean, of course, when I say equilibrium conditions, then this is a very simplified case where everything, for example, if you think about the population densities of atomic energy levels, if you have, as you call it, thermodynamic equilibrium, then all these level populations could be described by simply knowing the temperature of the plasma which you're looking at. And that can also be true for small regions. Then it would still be locally true. That's what we call then local thermodynamic equilibrium. It's a bit misspelled in this slide, sorry. But in the chromosphere, then this is not true even more any longer. And you can suddenly have situations where these level populations are influenced by radiation that originates from regions far apart, which makes the whole thing non-local phenomenon. And to really understand and interpret what you're seeing, you really have to consider the whole atmosphere at once. That is a significant complication from simple equilibrium conditions. That, in summary, actually makes the chromosphere a very challenging topic. And in that sense, numerical models are very important here because they can support us to interpret and understand what we're actually observing. Here you see the desperate attempt maybe to make a qualitative sketch, a qualitative picture of what we would see in quiet sun regions. And I mean, from this cartoon here, you really get the impression this is not what somebody would call quiet. There are already a lot of different ingredients that we know of from observations. There are a lot of waves of different wave modes propagating. We have many fields, and this wave will interact with these fields and many other things. And but we know for sure that the chromosphere is a very important and integral part of the solar atmosphere, and still we have a lot of open questions despite in this case decades of research. So it's still a hot topic nowadays. So what we have just saw from the observations is that the chromosphere is highly dynamic. We see a very intermittent and complex structure. There's a large range of spatial and temporal scales, and the whole atmosphere is coupled. That means if you want to make a complete model of, that describes everything that we observe, we have to account for these observations. We ultimately have to come up with a time-dependent approach, a time-dependent model. It should be three-dimensional to really account for this spatial structure. And the domain, the computational domain that we're simulating, should be high enough to include all the relevant spatial scales, and the resolution at the same time should be high enough to properly describe all the physical processes going on there. And as well, since the layers are coupled, we also need to include all layers, the height range that is relevant here. That's, of course, challenging. And there are, of course, technical limitations to what we can do today. Some of these model requirements are in particular very computationally expensive, and that has been limited by the available computing infrastructure, which of course has been improving over time and still is improving. So there will be more and more things that can become possible, and the models can be improved step by step. Of course, one doesn't want to wait until we have the computers that can do it all, but we want to progress, and for that we have to find practical solutions, and we have to go for some simplifications and approximations in the beginning. For example, we could reduce the number of spatial dimensions, the size of the regions that we are modeling, or also, of course, the resolution that we can afford. Then, of course, we can decide which are the physical processes that are most important and can leave away some processes that are maybe not so important in the beginning. And of course, it's also a matter of finding and developing very efficient numerical procedures. And as I said, over time, there will be improvements step by step. But those will not happen by themselves, but it's a very important point here to see that observations and models will always evolve or should evolve hand in hand. We have the observations give us constraints and things that need to be explained by a model, and at the same time the model helps interpret maybe the observation. But then also on the other side, the models need to be tested and either validated or maybe proven wrong, which is also interesting because then we know we have to work further on a certain aspect that's not reproduced correctly. But once we have a sufficiently realistic model, we can also make some predictions and can define certain cases or observations that should be checked in reality. And that is the circle that together will increase our understanding of the solar chromosphere. So as I said, there are technical limitations, and one has to start somewhere, right? So you can't have it all in the beginning. That's very painful, but it's just a reality. And so one has to decide how to simplify the model in the beginning. So what I have shown here is an illustration where you have on the lower axis something like the dimensions, the number of dimensions that you can afford, going from maybe 1D, a static 1D approach, towards a full 3D time-dependent model, which of course is where it should go in the end. On the other axis, the vertical axis, we have then the complexity of the physics that is included. It's going from a very oversimplified approach, very simple, to a complete description in the very end. And of course, one can make different choices. One can maybe go for a full 3D model, but then due to the limited computational possibilities and resources, one has to sacrifice physical ingredients. Or one is choosing to include as much physics as possible and restrict this to a 1D setup. Interestingly also, this depends a bit on what we know. Because we can define only our goals based on the current knowledge that we have. So with time, we will learn more and more. We will discover more things in the chromosphere that should be modeled. For example, the spatial resolution of observations, of course, is a limitation. And there are things we know today that we should include in the models that we, for example, didn't know about 50 years ago. So also the whole diagram that you see here is dynamically changing with time due to advances in the technical possibilities and discoveries that are made, and also the understanding that's gained. So in time, our knowledge horizon is moving further, and we're getting more and more towards a complete picture of the chromosphere, or at least we get an understanding of where we should be heading. And it's fair to say that we have come a long way already, just a few illustrations here. And in the following talk, I will also select a few examples to illustrate the progress we have made so far. Here are different simulation or modeling setups or approaches that you can consider, ranked again from very simplified to challenging. And one can distinguish here between theoretical modeling, which is starting from physical principles along, or you could also take another approach and base your modeling on observational data with the aim to reproduce the data as best as possible, and then see what this gives you in terms of physical model behind this. On the theoretical side, of course, you could start with 1D hydrostatic approach, but then one has to go further and include more dimensions. One will go for dynamic setup, 2D or 3D radiation hydrodynamics, then move further and even account for ionization, which we learned is important. And then finally, you also have to start caring about deviations from this ideal magnetodynamics assumption. Namely, you have to consider ion neutral effects, for example. And that's the current frontier where we are today with modeling this. And the next step, even, which is on the horizon at least, also if you want to go beyond this, one also can think about more particle, directly particle related properties, particle acceleration, for example, which is important for understanding flares. On the observationally driven side, you would again, you could construct 1D hydrostatic atmospheres by comparing them to observations. And another technique that's done a lot these days is data inversion, where you start with a temperature stratification or atmosphere stratification, and you adjust the observables that you compute with this until you fit all observations that you have at hand. And there are also a lot of progress has been made. Used to be pixel by pixel, so to say, from top in a quasi 1D setup, but development is going towards making use of the fact that neighboring locations in the atmosphere are not isolated, but they are connected to the neighboring regions due to by physical principles, physical mechanisms. So you can really make use of this and spatially and also temporally couple then these inversions and get much more realistic results from them. When we talk about spatial dimensions, I just want to make this as a simple example to show you what kind of considerations one has to make when constructing a model. So first one has to ask what kind of what's the small spatial scale that I really need to resolve here in order to accomplish my set scientific goals. And currently, there are numerical simulations which have horizontal grid cell size of about 1 to 2 kilometers. That's the current state of the art. But of course, there are also other processes which occur in even smaller spatial scales. Likewise, you have to think which is the largest spatial scale that has to be included. Typically, nowadays, it's about on the order of like a few thousand to 10,000 kilometers. But there are also simulations that go for supergranulation scales. So it's should be 100,000 or a few 10,000, maybe towards 100,000 kilometers. And this together then defines, of course, the number of grid cells that you need to really cover this domain with a given resolution. And currently, 3D models are usually about 512 cubed to 1024 cubed cells, which is what you can do realistically with also a fair amount of physics included. That will also always leave you also with some unresolved scales, and but there are some recipes that take care of this. There's some macro tricks you can do. You can apply some subgrid effects on that. Then the temporal resolution, temporal dimension is not fully isolated or independent from that. Of course, the dynamic simulations we have nowadays, they advance from a certain atmospheric state, time step by time step. And that is then set by the current Friedrich-Levy condition, which basically means the maximum time that you can afford to go from one state to the next is set by the highest speed of any, for example, wave mode that is used in your simulation, and the actual size of your grid cell. That means the time that a certain feature or some certain information needs to travel from one end of the grid cell to the other end of the grid cell. That is the time, the maximum time that you can afford. It's a time step here. And that also immediately tells you that if you go towards high resolution models and you make these grid cells smaller and smaller, then also your time step will get smaller and smaller. And you need a lot of time steps to cover a certain simulation time span. For example, you need to consider the dynamic timescales that are included in your model. If you have a compression zone in there, that evolves on time step for many hours. And if you really want to do a proper model, then you have to cover these durations with rather tiny time steps. So that's a very challenging thing to do. Typically, if you have no magnetic fields in the photosphere model, for example, you get away with probably on the order of 0.1 second or so, or even more. But as soon as you plug in some magnetic fields, especially with stronger fields, you will have, for example, phase speeds and other wave modes which propagate very fast, and that affects then your time step, and that can go down to milliseconds or worse. It is certainly challenging, and to make it even worse, in most codes, a certain time step, but the time step for the whole simulation is set by the smallest time step that occurs anywhere in your simulation box. That means if you have one single grid cell with an extreme event that has a very small time step, that would affect then the whole simulation. And that's of course something one has to either live with or come up with some smarter recipes. Here's an illustration of the effect of spatial resolution from default simulations. In the top left, you see an earlier model with a grid cell size, horizontal grid cell size of 48 kilometers, and then you go to the right, and then bottom left, and finally bottom right. And you really see the effect of increasing spatial resolution. In the closest case, you see these granules in the photosphere, but they are really roundish and almost look a bit artificial. But then if you go to the highest resolution, you start to see that the edges of the granules have a lot of structure which you couldn't see before. That also means there are a lot of physical processes going on that were simply not caught by the low resolution model before. So it certainly shows that it's worth going to high resolution. We can also do the same. Another example, this is from the Cobalt quote, where you see temperature slices in the chromosphere at the height of about 1,000 kilometers or so. And again, you go from smaller domain size, smaller resolution, lower resolution, to the lower left, which is a model from 2002, to a model that I currently got from Oscar Steiner, which has much higher resolution. And you clearly see that just by increasing the resolution, also you see more and more details in the chromosphere. These models are only hydrodynamic, but if you also compare this to a magnetohydrodynamic model here on the right-hand side here, which has started with a 50 Gauss initial vertical field, you see that also including the field has a strong impact on the structures that you see. You see now a lot of very, very small scale structures that you didn't see before, telling you that the field has a large impact on the structures you see. Then, as it goes for physical processes that need to be included, there's a long list of things, and with different priorities. Radiative transfer, of course, is a must. You need that, and then you have to describe the magnetodynamics aspect. Thermodynamics, of course, the equation of state, gravity, which is certified medium. Then those were probably are the basic things you really need to take into account, and then you need to also go for ionization, conduction, maybe chemistry, or even more important, ion neutral effects. As also said, there will be a lot of deviations from equilibrium condition. That is particularly true for the ionization degree or for atomic level populations, and also if molecules are important for your science case. The radiative transfer in the chromosphere is very challenging, and of course it's neither fully transparent nor fully opaque. It really depends on the wavelength. And you could see it maybe by means of the mean free path of a photon. If you're deep down in the dense convection zone, then a photon can't move very far from being emitted until it's absorbed again. So in those situations, you would get away with a diffusion approximation for the radiative transfer, which is a large simplification or makes it much easier to simulate this. However, if you come to the chromosphere, that doesn't work anymore because now it's partially transparent, and you're coupling, the radiation couples regions in the chromosphere that can be very far apart, so the photons can travel a long way between being emitted in one region and being absorbed again in another region. So this is a very non-local problem, and that makes it really, really difficult. In addition, if this couldn't be bad enough, you can also have then some radiation that's coming down from the corona, for example, not only from the photosphere up, but also down from the corona, which can affect level populations and can then affect the radiative transfer in the chromosphere. So one has to see or ask first, what exactly do we want from the radiative transfer for the intended modeling? Do we really want to reproduce details with the line profiles, or are we only interested in the impact on the atmospheric energy balance? And that's why we usually nowadays do this in two stages. First of all, we simulate the atmospheric state, where we're interested in the plasma properties and the energy balance, and then for a comparison with observations, we take another stage and use the transfer code to produce synthetic observables. Let me now briefly show you this. This is a very classic model, 1D semi-empirical model by Vanessa Abbott-Lösser from the F1, the VL model, but there are many more similar ones, the FAL, NSM-FA, many more. And what you are seeing here is the temperature stratification, with the photosphere being on the right-hand side, and you see the temperature minimum down there at 500 kilometers, and then you see the chromosphere and the sharp temperature increase in the transition region. What you do here, they constructed this by taking the stratification and calculating then the synthetic observables, the spectral lines and continua, and adjusting the stratification until they had an optimum match between their model and the actual observations. And they have included a lot of different spectral lines in the UV and even millimeter continua to derive this. This has been done to different types of regions on the Sun, and it's still usually a very good first model for some considerations, so it still has some educational value today. The limits are clearly it's 1D and it's static. And it also means it can, for example, not explain everything. For example, it has problems with explaining observations of carbon monoxide molecules, which we clearly see on the Sun, which cannot exist at the temperatures that are particularly small, which is clearly a problem. Next idea would then be to include go for dynamic models, to choose time and approach. Which you can see is the case in observations. And here's an example from Radincoat by Martin and Stein. And you see here the lower figure shockwave profile. So they treated a 1D atmosphere in a dynamic way by imposing a piston at the bottom of the atmosphere, which is actually driven by velocities that are derived from observations, and this produces shock waves that run through the atmosphere. And from that, then they can calculate synthetic observables, like you see on the right-hand side here, the line profile of the calcium line as a function of time. And the interesting thing here was that this actually could explain then observations of these calcium 2H grains that have clearly been observed, but that could not be explained in a static setup. So that's a big success of going towards more realistic models. Should mention also there are also, of course, many other models, theoretical models, Bodenschneider and so on. And but still, the overall limit here is 1D, and we clearly know we have to do something better to explain all observations. So a big class of models nowadays is includes modeling in 2D or better 3D. You usually choose a small part of the atmosphere. You include the upper convection zone, because the convection there is driving a lot of the dynamics, and you get then itself consistent model in the sense that you don't have to describe any dynamics. But then you have a certain computational grid, and you advance it time by time. Again, you have to solve the MSD equations. You need a realistic equation of state, and you need relative transfer. And there usually go for a somewhat simplified setup, or for example use pre-tabulated capacities. This is an example from also rather old 3D simulation. This is a vertical cut that you see here, and what is shown here is the logarithmic magnetic field strength, and you see the white line gives you the optical depth unity that's basically the bottom of the photosphere, and you see some green structures sticking out, which could be magnetic flux concentrations, which then expand in the chromosphere bath. And you see here also you can see some waves propagating there in the uppermost parts of this, and you see by going this step, which is a big step, computationally a big step, you already see a lot of dynamic phenomena that you also see in observations that you can try to understand based on this kind of simulations. If we look here at the, you have seen that before in one slide, but here in more detail, you see a cut through the chromosphere in gas temperature and at about 1,000 kilometers. And what you see here is very hot shock wave, shock fronts, and you see cool post-shock regions. So you have to understand that these shock waves that you're seeing are coming from below, and they're just cutting through this U plane as you see this. So they start as a small point, and then they expand these onion-like rings until they collide with neighboring shock waves. Now this picture actually has very interesting implications because it shows that you can have high and low temperatures coexisting in the chromosphere at the same time. And that then was good news for carbon monoxide. And you could, one work that was done more than 10 years ago was to consider a chemical reaction network where you have then 7 or 8 chemical species which are relevant in the chemical reaction network, that means chemical reactions that would produce CO, that are relevant for CO, and that you would plug into the simulation code. And you would then time-dependently solve the rate equations of this chemical reaction network. And the result is what we see here now. This is again a vertical cross-section. You see the convection zone in the photosphere and then the chromosphere. And the color-coded, the colors are the CO abundance. That means how much CO is there. What is the proportion of CO molecules in respect to the whole gas that's there. Red means there's a large fraction of CO, and blue means there's almost no CO. What you can see here is that there are shock waves that are flowing through the chromosphere and dissociating all CO molecules. But these molecules are formed quickly again once the shock wave has passed. And that clearly shows you that CO oscillations can then be explained as a part of this dynamic environment. At the same time, we have enough hot gas to explain the UV observations. When talking about 3D simulations, then I also have to go for mention, of course, BFOS. And this is just a quick summary of the features of BFOS. Again, it has variation, it has MHD, a realistic equation of state, but it also includes accounts for some non-LTE losses in the chromosphere and has an optically thin corona. That means also advancing in realism concerning the radiative transfer. And since it has corona as well included, you also need conduction along field lines. This is also taken care of. And the newer versions of BFOS will also have non-equilibrium hydrogen and now also helium ionization. And I will also show you the next steps based on this. Here's an illustration of a BFOS simulation that's publicly available. You will see the link in the top, so you can actually download data sets and look at them yourself. What you see here is an illustration of temperatures about 7,000 Kelvin. On the top and below, you would see a corresponding layer a bit further down. What you really see here is that you have some loop-like structures, so the temperatures outlining some of the magnetic fields in this simulation box. And the whole thing is very dynamic and evolves very on dynamic time scale. So this is very coming close to the impression that we get from observations. The simulations then allow you also to do all kinds of tricks and illustrations and really understand this in detail. Here I overplot as well main field lines. You see some of these, there are 2 patches of opposite polarity, and there are some loops forming which are connecting these, and these loops are reaching rather high up into the atmosphere as well. This is a corresponding model for the quiet sun, where you don't have these large-scale magnetic field structures, and that has a direct impact on what you see here. That means since there's no large-scale magnetic field, you don't have these large extended loops, but you have a lot of fields rather closing in very low-lying loops. And at the top of the model, you can have actually situations that you didn't have before. Namely, you can have high beta regions where actually the plasma dominates over the field and produces interesting dynamics there. Has to be seen if this is realistic or if this is due to the lack of large-scale structures here. This is the same simulation, just in a vertical cut. You see the gas temperature. You see clearly, or I hope you can see this, you can see some propagating waves, but you also see these peculiar pockets in the upper atmosphere with very interesting dynamics. Talking about the magnetic field itself is really complicated, and it's looking at the simulation shows you that you can't really get away with any 1D or static approach here. You really have to fully see the details of the magnetic field. And what you see here, this is a close-up, so it's only a small part of the simulation box from the Cobalt simulation. And you see it has a very complicated structure, and sometimes you see something rotating or swaying, you can maybe define some subgroups, but it's really continuously reorganizing, and it's very challenging to interpret this. The next step, which is currently
Sven, just keep in mind that your time is almost over.
Yes, and I'm almost done. So next step is then to include ion-neutral interactions, and here you see an illustration from work by Martinez Sikora, which was published last year in Science. This is still a 2D simulation, but this is the first visible sign that we're moving forward in this direction. And there you really take into account deviations from the ideal MHD assumption, which is clearly where we should be heading. The next step then, which is also being developed right now, is going for multi-fluid or multi-species codes. That is a version of BFROST, which is developed in this direction, where you really then start to treat maybe neutral particles or ionized species and free electrons as separate fluids. And then this way you can really much better describe these ion-neutral effects, which can have important consequences on the realism of your simulation. These approaches are in testing phase and early production stage, so I guess we will see some first results quite soon. The way forward is then to maybe combine some of these recipes that we have, especially if we want to go for self-consistent simulations of active regions, especially when we think about flare-producing sites. There we want to have something like particle acceleration, and that is computationally prohibitive still, I would say, to do this for a very large computational domain with all the ingredients that we just saw. But the dispatch simulation framework by Northland and collaborators may be the way forward, where you can combine different approaches defined on sub-regions of your simulation box, where they can actually run on different grids, on different resolutions, even different time steps, but still efficiently communicate with each other and give you an overall very advanced simulation as well. So I'm closing with just showing you the predicting power of these simulations. And this is what I said before. You have numerical models, and then you have the second stage where you would take a related tensor code and produce synthetic observables like this. And this is done for ALMA. And this is a slide where you see on one hand side, you see the gas temperature in the chromosphere, as shown before from the model. And the other is the intensity that you would observe at 1 millimeter from that model. And it's really difficult to tell what is what here, because the prediction here is that ALMA would be a linear chronometer of the quantum plasma, which has great diagnostic potential. And this is currently being worked on in Gregory Saturn's production and the Salmon network, where we want to develop these techniques further. Here again, you see this is another millimeter map which is based on this enhanced network bifrost model that I showed you, which we will also use as a benchmark to develop our numerical tools which we want to use in this context. This is just a quick example, just an illustration that shows you that the accounting for the ionization degree in non-equilibrium actually has benefits also in this context, because it doesn't, the information height of the radiation that we see here doesn't follow the gas temperature anymore that closely, but it's somewhat decoupled and gives less variation, and it makes interpretation also easier. Anyway, that's the last slide here on IMA. You see on the left-hand side, it was supposed to be a movie, a first impression from IMA observations in cycle 4. This is an early project, which is still currently under work to improve this. But the point I would like to make here is that IMA in a few years will provide observations of a few thousand spectral channels with cadence of 1 second maybe. And those will be data sets that will be very, very interesting for advanced data inversion techniques as well, where we hope then to get detailed models of the field dynamic structure of the chromosphere. I would like to close with this and just concluding that the chromosphere is still very challenging to model, and our simulations are still having a hard time. There are a lot of tough tests that we have to pass here, but we see clearly some progress, but there's also still a lot to do. Thank you.
Okay, thank you very much, Sven. It was very interesting, at least for me. And now we are open for questions and discussion. And basically, given that we have a manageable group of people, you can either like unmute your microphone and ask a question, and or give comments, or send me a request in the chat, whatever you want. Okay.
So, Gregory, do you have a?
Yeah, Dale, go ahead.
This is Dale. I just wanted to ask the question. I guess, have been getting reports that ALMA's brightness temperatures seem to be higher than the models are providing. I was just wondering how the observational constraints can get folded back into the models. What's sort of the avenue for doing that?
Yeah, that's a very interesting topic, and I think at this point, I think there are still some uncertainties also as it comes to the brightness temperatures, of course, derived from ALMA observations. And as you know, we have observations from last year and now it's May, but still properly processing the ALMA data and coming to reliable brightness temperatures. That's something that's currently going on. But it's also true that some simulations that we have shown somewhat lower temperatures, which was a bit surprising. But that points out that some of the simulations were still lacking important ingredients. For example, well, non-equilibrium ionization we figured out is very important, but also anything that affects electrons in the chromosphere will be very relevant also for a comparison with ALMA observations. So I think there's still a lot to be done, but I think this will also provide very interesting tests for the molecular models.
Dale, any follow-up?
No, thank you. That was a good response. Thanks.
Other questions? Hugh?
Yeah, I've got a question. It's about the timescales in the simulations. Of course, I'm interested in the particles, which is, I think, a future kind of thing for the atmospheric models, but still very important because the particles contain a lot of energy and momentum. the thing is, the particles are very non-local in their properties, and so they will drive the model resolution very strongly in that sense. But as you were speaking, it was very interesting. I was thinking, well, my goodness, it's not the particles that drive the models in this sense, it's the speed of light, because opacity, complicated structures, radiation transfer across in 3D, that really is the limit, isn't that right? So can you comment on how bad this situation really might well be for future modeling?
Yeah, I mean, also particles, if you think about particle acceleration, if you think about flares, which of course is this is goal to explain that, then you can have very, very high speeds. And as I said, that is something that doesn't make sense to try to simulate in a setup where these speeds would define the global time step. So you really have to go for some alternative recipes to handle that. And that's, for example, something that can be done with this dispatch framework, where you would then simulate most of the atmosphere with realistic modern 3D MHD code, maybe translation and so on. But you would then rather handle particle acceleration in addition in a separate way. And those reasons where it's very, very necessary, maybe with their own time steps, right, without affecting the rest of the domain. And you have to bring this together again. So I think there are a lot of numerical tricks that are necessary and that can be done in order to accomplish this. But that's really at the horizon currently, and I'm very optimistic that we will see very successful models in the future.
Okay, any more quick question? I see that everyone is muted. I will ask my questions during the follow-up in a week from now. And if you have further questions or someone else will have questions, please send me emails. I will ask Sven in the follow-up session and post online. This recording will be posted online shortly. And the next seminar will be given by Kirill Kuzanyan about solar dynamo and role of helicity in 4 weeks from now. So thank you very much for attending this event. See you in 4 weeks. Thanks. Bye.